Now we are going to design a doubly reinforced beam in which span of 8 meter is given and uniformly distributed load of 50 kN per meter is given. In addition to that, a cross section of 300 cross 600 mm is also given. M20 Fe415. First of all, we have calculated the maximum bending moment mu max by Ws square by 8. It comes out to a 400 kilonewton meter. Now, also calculated now the bending moment at the mu limit by considering the cross section mu is equal to RBD square and substituting value of B as 300, D as 600 and R is equal to 2.76 for M20 Fe415. The value comes out to be 298. That is the indication that the load bending moment resisted by the cross section of 300 cross 600 is much more less than actual bending moment, which was 400 and this is 298. So we have to design it for a doubly reinforced beam now. First of all, what we are doing for this bending moment of cross section of 300 and cross 600, how much area of steel is required, that we have calculated by using the bending moment as 298. Using the empirical formula, area of steel comes out to be 1715. I call this area of steel as AST1. Now, this is only for that 298. But balance, what about the balance in bending moment? That bending moment is 102. For this bending moment, which is balance one, we will again have to calculate the value of additional steel in the tension zone. We call it the area of steel AST2. And this AST2 comes out to be 513.6, but 0.87 Fy into D minus D dash. D dash is the cover at the top of the reinforcement zone. And it comes out to be 513. The total area of steel comes out to be AST1 plus AST2, that is double 229.26 mm square. I have taken 8 bars of 20 mm and then find out the total area of steel provided. It comes out to 512.8 mm square. Instead of that, I would have placed 3 bars of 22 mm, but I have not taken that into consideration just now. So area of steel provided is more than the required one. So our design at that part is same. But now here we will have to design for the area of steel in the compression zone by using D dash by D, that is the cover and the top in the compression zone over the entire depth, effective depth 0.08. From the table, FSC can be calculated with a ratio of D dash by D is 0.05, 0.1 and 0.15. It comes out to be 0.08. Always going on the higher side, we can find that this is 0.1 and the value of FSC comes out to be 353. Substituting the value of FSC and find out the balance moment for the compression zone, it comes out to be 525.36 mm square, say 600 mm square. Now, I am providing 3 bars of 16 mm in the compression zone, which is more than the required one. So our design for the compression reinforcement is also same. Now, once the reinforcement is provided, then we will have to apply for check. First check is for the check for shear. Find out the VU, that is the actual shear force, that is WD LE by 2. It comes out to be 200 kilonewton. Tau V VU upon BD 1.11 Newton per mm square. PT for that 2512 mm square. Find out, we have calculated 2512 mm square. It comes out to be 1.4 and tau C is 0.3 Newton per mm square. 0.37 Newton per mm square. That is the indication that tau v is greater than tau c but less than tau c max. So we'll have to design the shear reinforcement. We have to design the shear reinforcement for the balance shear force. Then we have first of all we have to calculate the balance shear force. The balance shear force is equal to actual shear force minus the shear force taken by the concrete, Vu minus tau c Bd. Tau c Bd, it comes out to 74,000 Newton. For this 74,000 Newton, we'll have to calculate the balance shear force is equal to 0.87 Fy Sv into d upon Sv, where Sv we are supposed to calculate the spacing of the vertical stirrups. Asv is nothing but the area of the vertical stirrup. I am considering the two-legged 8 mm Fy, and area Asv comes out to 100 mm square. Now substituting the value here for Vus, that is 74,000, 0.87 Fy is 415, we are getting the spacing as 294 mm center to center. I am reducing it to say on the safer side as 200 mm center to center over the entire length. Now check for LD. Now this is M1 is to be increased by 30% as per the IS code rule, page given in page number 44. And then find out the value of LD. LD is 12 times bar diameter or 600 mm, whichever is less. So 600, whichever is greater, sorry. So we are going for 600 mm. Now LD is nothing but 0.87 Fy into 5, and substituting these value over here, I can straightway come across and finding out the value of LD as 3200 and in 940 mm. So check for LD is right. Now check for deflection. PT we have already calculated, it comes out to be 1.4 previously. From this we have calculated the modification factor. Then ratio of span by depth ratio multiplied by modification factor should be greater than actual span by actual depth ratio. It comes out to be 18.0, which is greater than 13.33. We can say yes, our design is okay. So when all the checks are over, I have just drawn the figure over here showing the L section and the cross section with 8 meter span. Because 8 bars are there, so I have provided in the 2 layers, lower layer and the upper layer, lower tier and the upper tier, 4 bars on the lower tier and 4 bars on the upper tier, with a spacer in between the two of the same bar diameter has been providing over here. So if these are the 4 bars of 20 mm, these are the 4 bars of 20 mm, the spacer bar is also of 20 mm, and the spacing of this spacer bar is taken as minimum 1 meter so far. That's over and all. One thing again I will repeat. Once the cross section is given, keep in your mind, when the cross section is given, that clearly indicates we'll have to design this beam as a doubly reinforced beam. Thank you very much.